Hello, I'm presenting our work. Its title is DUI-BIO Depth Uncertainty Incorporated Visual Inertial Odometry based on an RGBD camera. Visual inertial odometry is a robust post-estimation method that uses the data of a camera and an IMU. It's essential to many applications, including the virtual reality, unmanned autonomous vehicle, 3D scanning, and robot navigation. In the literature, the monocular camera-based VIO has been extensively studied. It usually has an initialization process to recover the visual scale. The initialization process requires sufficient IMU excitement. It means that in the beginning, you need to move the device extensively in order to accurately recover the scale estimation. It's ill performed in degenerate motion conditions. For example, if only translation is involved. A quick remedy to that is to use a stereo camera or an RGBD camera. Since the RGBD camera projects IR pattern to the environment to enhance dense stereometry, its depth data is more denser than that of the stereo camera. And also its depth data is more robust under low illumination conditions. It's very important for some indoor navigation applications. So this work we focus on the RGBD camera-based VIO. And this line of research has not been extensively studied. Some EKF-based algorithm that lack initialization function to accurately estimate the wind's initial state. The other smoothing-based method has very sophisticated initialization function, but they assume the depth elements are accurate. That means they treat the features inverse depth as constant in the optimization process. However, the depth error is not trivial. In order to model the depth error accurately, we need to consider the uncertainty of the depth measurement. In other words, none of the previous RGBD camera-based VIO has considered the uncertainty of depth measurement in the initialization, nor the optimization process. This work we focus on to modeling the uncertainty of the depth measurements and apply them in the video inertial automation process. We have three contributions. First, we use a Gaussian mixture model to compute the values and uncertainties of depth and inverse depth. Second, we propose a hybrid PMP method to utilize the uncertainty of features to robust initialize the states. Third, we integrate the uncertainty of inverse depth into the optimization process. The general depth model for our RGBD camera's structure core is with two IR camera and RGB camera and an IR pattern illuminator to enhance the stereometry. We can get a dense depth image, and each depth value in the depth image can be transformed to the IR image through the transformation between the IR camera and the RGB camera. This is the standard stereo matching sketch at the depth at a pixel UV can be represented by this equation, and the inverse depth lambda UV are represented here respectively. The rho UV is disparity that generally assumed to have a Gaussian distribution with standard deviation sigma rho here. So accordingly, we can compute the sigma z, the depth, the standard deviation of the depth, and represented by this equation. The sigma lambda is the standard deviation of the inverse depth represented by this equation. We can see that the sigma z is quadratic to depth and the sigma lambda is a constant scalar if we assume the disparity, the sigma rho is constant. However, in reality, due to the noise, the measurement noise, and the quantization error, the error model of at a pixel UV is dependent on its neighbors. So to model this error, we use a Gaussian mixture model. Specifically, we assume each depth value in its neighbor is a Gaussian distribution, and Dij and its mean is d bar ij with standard deviation sigma ij. And this is our pre-calibrated the relationship between the sigma ij versus the Dij at different distance. We can estimate its standard deviation at that pixel. And by adding these neighbors together, and we can estimate the value of the depth d at uv, represented by this equation, where wij is the weighting factor of the variable dij. By doing this, we can compute the mean and standard deviation of the depth at uv by this equation following a standard Gaussian mixture model. Wij is the weighting factor. The first part represents the spatial correlation. The second part represents the depth similarity correlation. A log operation represents a Cauchy loss to reduce the effect of depth discontinuities. The detailed derivation can be found in the paper. Similarly, for inverse depth, you can also compute its mean and standard deviation for the inverse depth. We did some tests to compare their performance. So the color shows the scene where we get the data, and this is the result of the general depth model, and this is the result of the ground truth. The ground truth is obtained by capturing about 500 depth data at this location, and for each pixel, the mean and the standard deviation of each depth can be computed accordingly. And the last one is the result of the GMM model. You can see that the GMM model can produce more closer results to the ground truth than the depth model. Similar results can be achieved by comparing the inverse depth uncertainty as well. You can see the GMM can produce more accurate standard deviation estimation for the inverse depth as well. So the second part, we introduce the hybrid PMP. Before that, I want to go through a little bit about the pipeline of initialization process. Generally, we have a couple of camera frames as shown here in a sliding window. The first part need to find out 2 frames and use PMP method to compute their pose change. Based on that, the features are triangulated. So this is the basic of the whole video structures. So then next step to add the other frames one by one and to triangulate their features as well. After that, all the structure, including the pose and the features, are optimized together through a bundle adjustment process. Then use the IMU pre-integration by align the IMU's pre-integration with the video structure. The scale, velocity, pose, bias can be recovered. So the first step is crucial to decide the accuracy of the whole video structure. In WINS model, it uses 2D to 2D PMP method to recover the scale-dependent structure. In WINS RGBD, since it has depth, it uses 3D to 2D PMP that is called the ePMP method to recover the video structure with absolute depth scale. But we figure out is ePMP may not work in some cases like this. It's a Corello-like scenario. In this case, you can see we have 50 video features and only 7 of them have depth measurements. Under these circumstances, because the number of available features is so small, the ePMP can produce very bad pose estimation. To tackle this issue, we propose a hybrid PMP method. The key idea is to decouple the rotation and the translation. For the rotation, we use all the features using the 2D to 2D PMP method to compute the rotation, so we can get more accurate rotation estimation. And then we use the feature with depth to compute the translation. And this process can be boiled down to an optimization process by reducing the residue like this. The detail can be found in the paper. I want to point out that the W key here is a weighting matrix where it's computed from the convergence of the feature points, which is computed by the standard variance of the depth. That is the output of our GMM model. So we also carry out a simulation to compare the hybrid PMP with the ePMP. Each test we run ePMP with and without Gaussian using optimization, and hybrid PMP with and without Gaussian using optimization for 500 times, and the means, translation, and rotation are plotted. And each time we assume we have 30 features, and any of them have depths and with different number of the features. And the way to read this figure, you can see that, for example, we have 30 features and only 8 of them have depth data. We can see that the hybrid PMP with Gaussian Newton achieves the smallest translation error and the rotational error. For the third part, we talk about the optimization. So the nonlinear optimization is to reduce this cost function, to minimize the cost function. The first term is prior, second is IMU pre-integration, third is projection. The rho here is courtesy loss, and the projection is very standard. They have a feature of first observe the as post OI and track to OJ, and the difference between the measurement XJ and projected XJ head is the projection validity. For this term, it's called reprojection with depth. That is under the circumstances that the feature also has inverse depth of observation at OJ. In this case, we also want to penalize the difference between the projected inverse depth and the measured inverse depth with its uncertainty, the variance sigma lambda at here. And these two are computed by the Gaussian mixture model. The last term is called depth prior. This is the case when the feature also has inverse depth measurement at OI. So we want to penalize the estimates inverse depth lambda and its measurement using this term here. So we did some results here. We show a qualitative results, the comparison between the purple method with RGBD, WINS model, and WINS fusion. And you can see here, this is the data sets in a corridor environment. You can see that WINS RGBD fails in the fails to initialize because that's the number of available features in this scenario is small. However, our method can overcome this issue, and you can see that since the in the end we return to the start point, our method gets more accurate trajectory estimation than the other method. And for the second dataset, it is captured by installing the structure called on a viewed robot. And you can see that in the beginning, the WINS RGBD and WINS fusion failed to initialize, and only purple method and WINS mono is able to run the whole data sequence. And we use the motion capture to get the ground truth, and we can compare the trajectory with the ground truth. Our method is more closer to the ground truth than WINS model. And here is some quantitative results. We have 10 data sets. The first 6 is captured by hand-holding the structure call, and the last 4 is to install it on a robot. You can see that for the 10 data sets, our methods get small is the IMSE compared to the other 3 methods. And the second, we also catch 3 data sets in a corridor environment. Each time we return to the starting point, we use the EPN to evaluate the performance. You can see that our method achieves the smallest EPN error than the other 3 methods. So to conclude, we proposed a new RGBD camera-based VL method that incorporates the depth uncertainty for accurate WINS state estimation and applies hybrid PME approach for Rubin's initialization.